The last thing we look at in Calculus 1 is the idea of an antiderivative. And much of what you do in Calculus 2 will be working with computing these and finding their applications. The process of recovering a function f of x from its derivative is called antidifferentiation. Much like we could think of the derivative as an operation, something you can do to a function, the idea does carry over to antidifferentiation. So let's look at its definition. A function f is an antiderivative on f, or an antiderivative of f on some given interval, if whenever you take the derivative of the antiderivative, you get the derivative. So notice that the book uses capital letters to represent the antiderivative. So from here on out, if you see a lowercase letter in, for example, in these examples A, B, and C, the function is notated with a lowercase, which means this is actually the derivative. So what we want to do is now think backwards to figure out what is its antiderivative, or what was its original function. In order to do that, it's pretty straightforward, and we've actually even thought about this a little bit before. So if you're given the derivative is equal to 2x, what was your original function you had to start with to get there? Well, that means capital F of x is equal to x squared. And that is simply because if you were to take its derivative, f prime of x is equal to 2x. And we can continue in this matter, and then, for example, b, g of x, well, we're given the derivative is equal to cosine, so the antiderivative should be sine of x. In order to make sure, just take the derivative of g of x, and indeed we do get cosine of x. Now these two were very basic functions where we really didn't even have to think about the chain rule. But here in the case of C, we actually have a sum of functions, and indeed we actually have something going on where we have a composition here at the last case. So when we see a sum, we realize when you take the derivative, you could take the sum of each part or take the derivative of each part separately. So we could actually do the antiderivative the same way. So capital H of x, well, what derivative gave us 1 over x? Well, that was ln of x. And we can't just say ln of x because realize we don't have any given interval here. So what we have to remember is that a natural log or any log function cannot take a negative as its input. So we have the absolute value of ln of x, or the ln of the absolute value of x. And now in the second case right here, well, we have to actually do a little bit more thought. So here we know that the derivative of just e to the x is equal to e to the x. But what is going on with this 2? So original function was e to the 2x, and I'm guessing that that 2 came from whenever we had to do the derivative of 2x, which is the composition. Which indeed, the derivative of 2x is just 2, giving us the desired 2 right here. So that is the first basic examples of the antiderivative. But what we did neglect here is to realize or to even note that the function, for example, x squared plus some constant also has 2x as its derivative because the derivative of the c is just equal to 0. And a little typo here, it should just be without the apostrophe because this is not, it is. But anyway, recall that from section 4.2 we discovered that the two antiderivatives of function differ simply by an arbitrary constant. Arbitrary simply meaning that we don't care what one is because the derivative of a constant, as we have figured out many times, is just 0. We did do this briefly before. That is that if you are given the antiderivative, then the most general derivative of the function on an interval is just the antiderivative plus a constant. So it may not be good enough to actually just say plus a constant. We're going to be given some conditions we're able to find c. So if we know that the derivative, remember the lowercase means that we have the derivative, we have to work backward to find the antiderivative capital F of x. Well, its derivative here is just going to be equal, or the antiderivative here is going to be equal to x cubed, because indeed capital F prime of x is equal to the 3x squared, which we were given as our f of x. So we know that f of x is not just x cubed, it's x cubed plus a constant. But we're given this condition right here on the right that this x is in here, its value is 1, and whenever x is 1, its y value is going to be negative 1. So just using these ideas with the given or the found antiderivative, we find that f of 1, which is equal to 1 cubed plus a constant, is equal to negative 1. Therefore, 1 plus a constant is equal to negative 1, aka constant is equal to negative 2. So our true function f of x that satisfies the given conditions is equal to x cubed minus 2. So, and you can see this specifically can be seen right here as the certain function that satisfies that condition. And the set of all of these c values, you'll start realizing the word thrown around is the word family. So each of these that differ by just a constant is actually considered a family of functions. Now there are several rules that we can use to find the antiderivative given some derivative. So this function here is given to us is the actual derivative, and to find its antiderivative, there's a relationship between constants given as part of the derivative. So we have these rules right here, and we have the definition. So what you're going to see as you work through Calc 2 is this form of the antiderivative much more often. The collection of all antiderivatives is called an indefinite integral. So the reason is because the indefinite is because we're going to be having its value to be plus c, as you can see all those above. After you take the antiderivative, you add a constant to it. The definite integral is when you're actually able to find that, and there's many different techniques to do so in Calculus 2. This symbol right here in front is called the integral sign. Much like we were using dx over dy to indicate the derivative, this integral sign indicates that we want to take the antiderivative. Its function, the argument of the antiderivative, is called the integrand. And this dx right here is a differential. So dx, as the blank down here below, is a differential. And what it does is it indicates the variable of integration, which is important. As you look at applied problems, you want to know what is your independent variable. So as a side note, that this dx right here is going to, remember, deals with your independent variable. And that really does show up a lot more in Calc 3, where you're working with 3 variables at once. So with that being said, let's go on and use these rules in the context of several different examples. So now let's go ahead and look at the actual formulas and see just an idea how they work. So in example A, we're going to actually be dealing with a polynomial function, or something in the form of the x to the n, where we take the antiderivative with respect to x. So when we take the antiderivative with respect to x, as on the previous slide, we have 1 over n plus 1 times x to the n plus 1 plus the constant. And of course, n cannot be equal to negative 1, else we have actual rational functions, and we know that we have different derivatives to work with there. So when we look at this case, n is equal to 5, so its antiderivative is just going to be 1 over 5 plus 1 to the x to the 5 plus 1 plus a constant. So what we have then is just 1/6 x to the 6 plus c. And indeed, if you take its derivative, you can start seeing where those k's are coming into play, because it allows some cancellation between the constants. Now let's go on and look at the second example right here. In the case of B, we're asked to find the antiderivative of 1 over the square root of x. Well, let's go on and just first turn this into a form that we're more able to work with. And that is, we're going to take the antiderivative of x to the negative 1/2 with respect to x. So now its antiderivative is just going to be 1 over negative 1/2 plus 1, and then times x to the negative 1/2 plus 1 plus a constant. Simplify a little bit. We have 1 over 1/2 x to the 1/2 plus c. And then lastly, that gives us just 2 times the square root of x plus the constant to be the antiderivative of b. So we have a few more examples right here, and what I do is I encourage you to pause for a sec and go on and work out these examples before you look at the solutions, which will appear here in the next few seconds. Now to see some of the rules that we used with antiderivatives or with derivatives in the context of antiderivatives, let's go on and just look at the general antiderivative of this given f of x equal to 3 over the square root of x plus 2 sine of x. Well, just like we talked about earlier, you could take the derivative, and when you take its derivative, you take it one piece at a time. But we also have the negative rule, which means that you could plot negatives, which are very much related to the constant rule. So what we have here is actually 3 different parts. This f of x is actually equal to the sum of, let's call this first one, lowercase g of x, because this is still the derivative, plus lowercase h of x, because 2 sine x is the derivative. So when we take the antiderivative, we find that capital F of x is just equal to 3 times 2 square root of x. We found that the antiderivative of g of x on the previous slide. And then sine of 2x, well, that's just equal to minus 1/2 h of x. Minus 1/2 cosine of 2x, and then this is still plus a constant. So what these rules are basically saying is, well, you can see in the case of this 3, it was a constant of the original function. So this antiderivative here is 3 times capital G of x. And then we have just plus h of x. Be careful, because this negative 1/2 is actually part of the antiderivative. And of course, we still have plus a constant. So in context of just the actual simplification, we have 6 square root of x minus 1/2 times cosine of 2x plus c. And now let's take a little trip on a hot air balloon and figure out what type of calculus is going on there. Told you, there's calculus everywhere. So the hot air balloon, ascending at a rate of 12 feet per second, is at a height of 50 feet above the ground when a package is dropped. Hopefully that package doesn't hit anyone, but how long does it take for that package to reach the ground? And we can also assume the acceleration of gravity near the surface of the Earth is 32 feet per second squared. Assume no other forces are acting on it, such as air resistance or anything in that scenario. So let's look at what we're given. Well, first of all, this rate of 12 feet per second, this is actually a velocity. It's a velocity, namely note, at time equals 0. So at the beginning of this problem, this idea that we're looking at, or this scenario, we know the velocity at 12 feet per second at time equals 0. Then height, well, height of 80 feet, well, that's actually a position. And we know velocity, position, and even acceleration are all related depending on what derivative you're looking at. So this is actually an example of a differential equation. More on the terminology here in a sec, but let's just go on and think about what we have. Well, we know that laws of nature give us this differential equation, namely differential equation. In this case, it is dv, the derivative of velocity with respect to time, is equal to negative 32. In this case, it's going to be feet per second squared, but we're more concerned about the negative 32 in this context as our function. And it's negative because we're going down. And, well, we're also given a bunch of other information. So this is a differential equation, just simply because you could find its different or can find its antiderivative. And then you also are given some initial information. Initial value, in this case, was given to be that the velocity at time 0 is equal to 12. And it's good to note that the position at time 0 was equal to 80. So let's go on and use this and see if we can get an equation in terms of time that allows us to figure out how long it takes for the package to reach the ground. So I guess we could really say these are our initial values. So first of all, let's go on and work backwards. So the antiderivative of velocity or acceleration would just be, well, the ds of dt or v of t. And in this case, it's negative 32 t plus a constant. And we now use the initial values to find that constant. So we know that v of 0 is equal to negative 32 times 0 plus c, and that is given to be just 12. In other words, c is equal to 12 in this case. So our velocity function, v of t, is equal to negative 32t plus 12. Now we actually have another differential equation, because remember that this is just the change in time with respect to t. And now let's go on and we'll do it one more time and figure out what the position function is by taking the antiderivative of the velocity. The position function would then be s of t, which is equal to negative 16t squared, just using that formula from before, plus 12t, plus a constant. And like before, we were given that position at time equals 0. Well, it was negative 16 times 0 squared plus 12 times 0 plus 80. I'm getting ahead of myself, plus c is equal to 80. Therefore, we find c is equal to 80. So our position function could be written as this, that s of t is equal to negative 32 t squared, negative 16 t squared plus 12t plus 80. And we want to find out what it looks like, or we have to think about how long does it take the package to hit the ground. Well, the position of the package will be whenever s of t is equal to 0. So what we now have to do is solve this for the t values. So this one I would just suggest using the quadratic equation or the quadratic formula. Well, the quadratic formula will give us, for our values of t, that t is equal to approximately negative 1.89 and also 2.64. Except for it doesn't make sense to talk about negative time, so we could cancel that out. And it takes approximately 2.64 seconds for the package to reach the ground. As mentioned before, that problem we did was an example of using a differential equation. In the previous example, dv over dt is just called a differential equation, as I mentioned, just because we can actually find its antiderivative. This type of equation is solved by finding an unknown variable, v of x, in this case it was velocity, whose derivative is dv over dt, i.e., that is finding the antiderivative. So what we need to do is fix the problem of having an arbitrary constant by stating some initial values or initial conditions. And then these types of problems, based off of the initial conditions or because of the initial conditions given, are called initial value problems. Note that there is a general solution to these differential equations, and a particular solution given when we have specific initial values given. There is a whole branch of mathematics used to actually find these in many different techniques as you have more complicated functions.